that is dynamics and that is possible phases, and also that connect to the developer cosmology. And we have a better understanding of quantum gravity through string theory, and it's a surprising properties that the string theory development now actually trying to could be applied to different fields. So this connect to rising the tendency of the culture of the particle theory development, which is there are many powerful connections between different ideas and between different interdisciplinary, and also develop move the modern mathematical movement. So how can we think forward based on what we have right now? So I would like to use this hierarchy and dimensionless example to demonstrate that how we might be able to think about this. So the hierarchy and dimensionless, they are actually a dual situation. So one easy way to describe this is that the Higgs mass and the electroweak scale is extremely smaller than the Planck energy scale. So this actually also related to when you try to calculate the correction of the Higgs mass, and you see the divergent quadratic divergent property, and one natural way to solve it is you can introduce some new particle which can cancel this quadratic divergence, and then give you a finite small number of the Higgs mass. Okay, so this kind of hierarchical problem, and as I mentioned earlier, that there are two nature solutions, and the Technicolor, the Technicolor, it has a famous prediction that we probably will not find any low mass Higgs, but because now we find it, so the original Technicolor is now we can say that it's hit a big wall to a dead end. However, we can still make it alive in a way that you can require more sophisticated composite Higgs model. So you can still try to make it be consistent with the existence of this light scalar particle. And the discovery of these light scalar particles actually put us into a route that prefer to have a weakly scale, weakly coupling scenario. And for example, the famous theory of supersymmetry. However, if you calculate the Higgs mass under the supersymmetry, at tree level, the mass is preferred to be less than the Z-Boson mass. So if supersymmetry is right, and we know that it cannot be just like the simple form, and it will not be just fully nature. And what you can do is that you can add the radiative corrections, and you can leave the Higgs mass. But let's make the reference of nationless argument to of a simple symmetry to put some tension on that. So this is a flow chart put on by Nathan Steinberg. So the option of the nationless argument and what would be the different scenario in large hadron collider. So if we find something beyond a scalar Higgs, okay, and then we can check if the electron is breaking nature by putting into these new particles. And if the answer is yes, then it will be nature, and that's the most welcome scenario that in terms of philosophical thinking that the nature is beautiful. Yeah. Otherwise, if we cannot find something beyond the single Higgs, or even you find this additional new particle, but it cannot match to the scenario to make the nature, then we will force to abandon this kind of naturalist argument. So how this naturalist argument actually played a role in terms of particle theory development? Yeah. So this actually has been a while that when the theorists trying to build the theory model, this is has been a guideline, like you want to, the nature might not be preferred, it has requires some fine-tuning, like split supersymmetry, or the nature reveal itself in a simplified, more simplified, and this form will be more comparable. So if in the electroweak sector, then we find that the Higgs or electric symmetry breaking is unnatured. Okay, so then this will put us to think about the other scenario, because we know that the hierarchy is not just in the electric sector, not just on the electric scale, the Higgs mass compared to Planck scale. We have a hierarchy in also the other sector, like the quark and the lepton sector, and we probably would move to another direction, like the naturalist argument based on naturalist principle to build the theory might not be the way we want to go. Okay, so this will be a big deal. Like in Large-Hadron Collider, this might change the way we think of the theory. So then, how do we proceed? Like the flow chart I showed in the previous slide. How could we try to examine this all these big questions, all these ideas? So the way we do is that just do it. Yeah. So in terms of an experimental list, what we are going to do right now is that we discover the Higgs at its roughly half design energy. And starting from next year, we are going to run the full machine in the full energy mode. Actually, we will probably still start with the 13 TeV instead of 14 TeV. So what we are going to do is trying to fully understand the standard model precondition to prepare ourselves to establish the environment that we can verify there's a new physics disease or not. So for that, we will have to understand all the standard model process is considered as a background for new physics. And we will prepare all the tools in terms of the experimental tools and also the theory tools to calculate and verify those the standard model background. And we will try to push the standard model to the extreme, to the higher energy or the real production. So by doing this, then this is the realistic way that we can try to examine all the questions we just quoted in previous few slides. Yeah. So to me, like it's kind of a dream machine that all the dream era I have right now. Like I've been graduate, get my PhD for a decade, and I still feel like I'm very excited to welcome my each day in tomorrow, because there will be all exciting new progress moving on. Okay. All right. So then basically I complete the big picture about the physics of the large hadron collider we will try to do. So the next I will move on to what does that mean, hadron collider physics. Okay, so there's actually something that beyond what we have learned from the quantum field theory or the basic QCD or QED calculations. So let's start with that. By the way, can you remind me how much time I have? Half an hour. Okay. So the particle collisions, I start from here because in order to study the deepest layer of matter, what we need is we need a probe with the highest energy, which sounds just trivial. But how do we do that? In terms of a hadron collider, there are two important parameters you have to know. One, how do we define the energy? Okay, so energy is simple. You have two objects, just try to make it collide, and then we also have learned that the center of mass energy, you can use less energy to achieve the equivalent high mass scale compared to a fixed target experiment. Okay, so the other thing is the luminosity. So you have to keep in mind that when we accelerate particles in the accelerator, we are not actually accelerating single particles. We are accelerating a bunch of the group of particles altogether. So it's like a train. And then what really interact in collision is two bunch of the group of particles. They cross each other. And some of them have a ability to interact with harder scattering. So we often define a unit, which is the number of particles per unit area per second, as the quantity we can describe how much interaction has happened. Okay, so we call it velocity. So here, just put you some number about what's the typical scale of the luminosity we talk about. So you can see that from the 7 TeV collision to when we ramp up to the ultimate target luminosity of a large hadron collider, the instantaneous luminosity is a 2 order of magnitude enhancement. Okay. All right. So this is an evolution about the hadron collider energy as a function of time. Yeah. So it was a linear. It's a log scale increase of the energy of a hadron collider. Then you can see that there is a tendency here that when it's more difficult to move energy beyond this log scale because of the limit of technology of the magnet. And the energy frontier right now is a Large Hadron Collider. It is underground in Geneva, near Geneva Lake, and it has 4 major experiments. Okay, and ATLAS and CMS will be the one that I describe more in this lecture series. So the LHC itself is not just what you see, a huge 27-kilometer proton ring, and you have 2 protons just running in counterwise and clockwise direction for collisions. But before you can actually have the proton reaches higher energy put into the storage ring, you have a 4 stage of the acceleration, yeah, to stage by stage bring the proton to its high energy and also with high density. So the important components I mentioned earlier, which is the magnet. So for each LHC magnet, it has 2 channels that you can run the proton in 2 different directions. Okay, so this magnet of the acceleration LHC, it's about 8.3 Tesla, and we have roughly 1,200 magnets put around all the LHS tunnel. Yeah. Each one is 15-meter long. So to operate that, it has to be using superconducting coils. And technically, we built the largest cryogenic system in the world. And the acceleration gradient is 5 megavolts per meter. Yeah. So in terms of proton collisions, this is the modern view about the proton. And the proton is not just composed of 2U quark and 1D non-type quark. So the proton is also composed of, other than those 3 valence quark, it also composed of other C quark. So when we talk about the proton collision, we actually talk about they have either quark-quark, or quark-anti-quark, or quark-gluon or gluon-gluon interactions. So to think about how the proton collision happen, you actually have this cartoon view. You have 2 protons, and they all fly crossing each other. But one of the fundamental particles composed of those protons, they interact. Okay. So here is one example. You have 2 quark-gluon objects. They have hard interaction. They produce a TT-bar quark. Okay. So we have to build a model to describe these kinds of interactions. So to describe that, we first start with you have a proton accelerate to the energy that we designed. So in terms of ATV collisions, you have 2 protons with a 4 TeV energy. Okay, but the subcomponent of proton, they might carry just a partial energy of the total proton energy to participate in interactions. Okay, so we define a quantity which is just the ratio of this energy of this subcomponent object with respect to the total energy of proton. And you have 2 protons with 2 partial energy, they interact. So they mostly accelerate along the z direction. So the z direction is defined as the beamline directions. So if you just write down the full vector of the 2 objects, and you calculate the central mass energy of the interaction, hard interaction object, then you can basically have a quantity, the product of the partial energy fraction times the total central mass energy of proton, take square root. That's basically the central mass energy of the hard interaction system. So now you have a different object in this proton. We actually have a technical term for it. We call this sub-object as a parton. So they are the composition of the energetic proton. And we have an empirical function can describe what's the parton density function for each type inside the proton with a given partial energy and also the momentum transfer. Okay, so in order to calculate interaction production cross section of a proton collisions, we can write down a formula like this. So you have a parton density function from one proton and the other parton density function from the other proton, and then you have the dynamics, which is the hard scattering physics that you can calculate using the probability theory. And then you integrate over all the possible energy fraction of those 2 particles. Now you sum up all the possible combination, the quark-gluon combination. Then you get your final cross section. So up to this stage, I basically present you how you could calculate production cross section in the Hadron Collider. And one interesting here is that this hard interaction is something you can calculate with your favorite probability theory. And you have a part that is a soft physics that you don't know how to calculate. So currently, when we talk about hadron collider physics, we actually have one component that purely coming from the empirical measurement. Okay. So here I just show one example about how the parton density function looks like as function of energy fraction it carried inside the proton, and for different type of partons. Okay. So now we can actually rewrite this cross-section function. Just focus on this part. You could rewrite it in a way that the cross-section is the hard scattering part times the radial part, and we calling it a name as a parton luminosity. Okay, so you have a parton luminosity multiplied by the hard scattering, and you integrate over all possibility, then you get your final cross-section. So it's interesting to look at the probability of parton luminosity. Oh. So here shows a parton luminosity as function of the central mass. As I mentioned earlier, the central mass of the system is the square root of the energy fraction of each parton, their product, times the total energy of the proton collisions. So this plot is already fancy. Let me guide you through ATV. That's what we have before 2012 collisions. So the blue is the gluon-gluon. So you have two gluon partons that interact. And the red is the sum of all the quark and anti-quark interaction. And you can see that for the lower invariant mass system, that is, you have a parton carry less energy component from the proton. The parton luminosity is basically dominated by the gluon-gluon interactions. Yeah, and compared to the quark and anti-quark. But when you go to the high energy, so you have some turning point around the TeV scale. After TeV scale, the quark and anti-quark luminosity become dominant. Okay, so the other interesting thing you see that when you increase the energy of the proton equations, and both the gluon and the gluon and also quark and anti-quark parton luminosity they increase. And if we try to look at their ratios, so this is just exactly the same plot. The only difference from previous slide is I just calculate the ratio of the parton luminosity with respect to the ATV. So I use ATV as a guideline. So here, let me look at the red curve first. So this tells me that the 7 TeV collision parton luminosity is less than the ATV. Okay. So and in particular, when you go to the higher mass, this ratio is even higher. Okay. So this tells me that if you have interactions or a new particle at high mass, when you raise the energy of the proton collisions, you have a larger enhancement of the production cross-section compared to those low energy particles. Yeah. So the other thing is that now we are going to move on to the 30 TeV in 2015. So just take one example. If I have a graviton at 2 TeV, okay, which is instead of graviton, let me take one example. The KK gluon, for example, and if it can be produced through the gluon-gluon interactions, then you could see that the production cross-section compared to the ATV is a factor of 10 larger. Okay, so I just increase my energy, both proton collision energy, roughly factor of 2, but my production cross-section is a factor of 10 enhancement. Yeah, so that's why we are looking forward to build an even higher energy collider. And now, if the new physics happen at even higher energy, 3 TeV or even beyond, now you can see the 3 TeV is already almost a 2 order of magnitude cross-section enhancement. So the cost of building an even higher energy compared to the enhancement new physics opportunity. This is very good investment. So this is a busy picture, just to give you all the different, just put you a real physics process, production cross-section, as function of different collision energy of the hadron collider. And this stage line is the LHC energy that what we designed at the 14 TeV. So I just try to guide you through one example. Let's take a TD bar and the W plus W minus interaction, the production. Okay. So the TD bar is basically dominant. So you can see that the TD bar cross section potentially enhanced as you increase the Coulomb collision energy. WW is the same, but TD bar enhancement is much faster than the WW. Okay, so if you try to enhance from previous energy frontier tevatron, to the LHC, yeah. So the TD bar enhancement is almost 3 orders of magnitude larger. Compared to WW, it's only roughly 1 order of magnitude larger. So the major difference is that, as we learned earlier, that the TD bar is Coulomb dominant, and Coulomb velocity actually the enhancement is much faster than the quark dominant process. Okay, so now it looks like we have a nice setup about how we think about hadron collider physics. But other than you need to put some empirical description of parton density function to describe the parton dynamics inside, so parton kinematics inside the proton. I need to tell you some other bad news or some challenge of a hadron collider. And this is a picture we mentioned earlier, like you have a hard connection happen here. You usually describe the parton density function. So then you can complete the cross-section calculation through this function. But there's actually more than that. So for the quark, actually, it's very easy to radiate the gluon. In particular, not a soft gluon when the quark move in a vacuum. So this kind of additional radiation, before you have hard scattering, we call this higher order correction. So you have 2 gluon radiate from the complete production line, and you need to calculate next order corrections. So other than that, in the hadron collider, actually, you need to consider the hadronization of the quark and gluon. So the fundamental description of the final state of the quark gluon is not free particles. Yeah. So the quark gluon, they turn into pions, kaons, these mesons, or baryons, protons, neutrons. Quite fast using QCD time scale. So we call this process hadronization. And the picture here is actually what it looks like when you have simple, this is simplest interaction in the hadron collider. So you have a hard physics, and you have a lot of initial radiation. You radiate out gluon from the initial state quark. And all those quark and gluon, they eventually hadronize. Yeah. So this is a complete picture about how our current and effective description of one single event happened in the hadron collider. And this is not the full story. I here introduce you other one event, which is remember that you have also other partons inside the proton. So all of them also have opportunity to interact. Yeah. So, but before they interact,